Exclusive. OR is the smallest problem that breaks the smallest network. Put the 4 inputs on the corners of a unit square. When the 2 inputs disagree, 1 and 0 or 0 and 1, the answer is 1. When they agree, 0 and 0 or 1 and 1, the answer is 0. So the 2 corners we want to call 1 sit on one diagonal, and the 2 we want to call 0 sit on the other. Now hand this to a single unit, one sigmoid on top of a weighted sum, and ask it to get all 4 right.
How do we know it fails? Maybe the right weights are just hard to find.
We do not have to search. We can write down exactly what success would demand, corner by corner. At the origin, the weighted sum is just the bias, and we need that corner to read 0, so the bias must be negative. At the corner where only the second input is on, the sum is the second weight plus the bias, and we need a 1 there, so that has to be positive. By the same reasoning, the first weight plus the bias must be positive. And at the far corner, the first weight plus the second weight plus the bias must be negative, because that corner reads 0. Now just add the 2 middle conditions together. The first weight plus the bias is positive, and the second weight plus the bias is positive, so their sum is positive 2. That sum is the first weight plus the second weight plus twice the bias. Move 1 copy of the bias across, and you learn that the first weight plus the second weight plus the bias comes out greater than the negative of the bias, which, since the bias is negative, is a positive number. But the 4th condition demanded that very same quantity be below 0. A number cannot be positive and negative at once. No weights satisfy all 4. One straight cut can never separate 2 corners that sit on a diagonal. This was Minsky and Papert in 1969, and it stalled the field for over a decade.
Fine, 1 layer is too weak. Why not just stack more linear layers until it is strong enough?
It is the obvious move, and it is worth taking seriously. Here are 2 linear layers, one after the other, and nothing between them. The first maps 2 inputs up to 8 numbers. The second maps those 8 back down to 1. More parameters, more depth. Surely that has to bias something. Let us just follow the algebra and see. Feed the input through the first layer, and you get a weighted sum plus a bias. Feed that through the second layer, and you get another weighted sum plus another bias. Now multiply it out. The second layer applied to the first is 1 matrix, times another matrix, times the input, plus a combined bias. But a matrix times a matrix is just some other matrix, and a bias plus a bias is just some other bias. So the whole 2-layer stack simplifies to a single weighted sum plus a single bias. It is 1 linear map wearing a costume. So 2 affine maps composed are exactly 1 affine map. Stack 10 of them and it collapses just the same. Without something nonlinear between the layers, depth buys nothing at all. The stacked model is still 1 straight cut through the space, and exclusive. Or is still sitting there, still impossible. The problem was never that we had too few layers. It was that every layer was linear. Here is the entire fix. Take those 2 linear layers, and slip 1 nonlinear function in between them. In Scratch, and that is a hyperbolic tangent, a tan, applied to each of the 8 hidden numbers. Nothing else about the network changes. Same 2 linear layers, same inputs, same output. 1 function in the middle, and the collapse we just watched can no longer happen. 2 affine maps with a bend between them do not simplify into 1.
How can a single hyperbolic tangent in the middle change everything?
Because it bends the space, the second layer gets to look at. The first layer and the hyperbolic tangent together warp the input plane, stretching and folding it. The second layer still draws only a straight cut. But a straight cut through a folded space, unfolded back to where we started, is a curved boundary. The nonlinearity is what lets a straight decision come out curved. That is the whole trick, and it is the difference between a model that can do exclusive, or and one that never could. You can even read what the hidden units learn. With 8 of them to work with, the network does not need anything clever. One hidden unit can lean toward the inclusive or of the 2 inputs, firing whenever either one is on. Another can lean toward the and, firing only when both are on. An exclusive OR is simply the first of those minus the second, on when at least one input is on, but not when both are. The hidden layer builds features, and the output layer reads the answer off them. So here is the whole multi-layer perceptron, in one line of construction. A network is a list of layers, plus a loss. The list is a linear layer, a tan, and a second linear layer. The loss is sigmoid with binary cross-entropy, exactly the one we used for logistic regression. There is no new class here, no special multi-layer object. The depth is just 3 items in a list instead of 1.
But surely a deeper network needs a new backward pass, more layers, more calculus.
That is the natural fear, and the answer is no. Not one line changes. Here is the backward method, the same one from episode 2. It asks the loss for the gradient at the output. Then it walks the layers in reverse and hands each layer that running gradient. Every layer knows how to turn the gradient at its output into the gradient at its input, and to stash its own parameter gradients along the way. A 3-layer network just means the loop runs 3 times instead of 1. Sit with that for a second, because it is the quiet payoff of the whole design. We derived the backward pass once by hand for a single layer. Every layer speaks only about its own local derivative, the tan about its slope, the linear layer about its weights. The network just chains those local answers together in reverse. Adding depth is a longer walk backward and nothing more. Nothing else changed. Now let it train. 4 points, the same reverse walk over and over. The weights nudged a little on each pass. Watch the boundary bend into shape. The network wraps the 2 1 corners into their own region, a shape no straight line could ever draw. This is the exact argument inductive biases opened on, that a network computes numbers. There we used exclusive OR and a hidden layer to motivate the whole tour, and here we make the hidden layer actually learn it, and watch the gradient do the work. The impossibility from the start of the episode is now just a trained network.
Does this only work on a toy like exclusive? Or does the same code scale up?
The same code, unchanged. Here is the digits model from the examples. 64 pixel inputs, 32 hidden units with a hyperbolic tangent, 10 class outputs, and a softmax cross-entropy head. It is the same 3-line pattern you just saw, only wider. A linear layer, a nonlinearity, a linear layer, a loss. Trained on the real 8 by 8 handwritten digits, that same little stack learns to tell them apart. One honest word before we celebrate depth. There is a theorem, universal approximation, that says a single hidden layer made wide enough can approximate any continuous function you like, to whatever precision you want. Read that carefully. It means depth is not required for possibility. One fat layer can, in principle, represent almost anything. What it does not say is that one layer is efficient. Many functions that would need an astronomically wide single layer are cheap to build from a few thin layers stacked. So depth is about economy, not possibility. We reach for it because it is cheaper, not because it is the only way. We never trust a gradient we did not check. So we end where this series always ends, on the deepest network we have built yet. 2 inputs, 8 hidden units, 1 output, with a tan in the middle. Run the gradient checker on it, the same one from episode 2. It has one job, to make sure the calculus we wrote by hand agrees with reality. Here is what it does. For every single weight, it nudges that weight up by a hair, measures the loss, nudges it down by a hair, measures again, and reads off how fast the loss actually changed. That is the numerical gradient from finite differences. The analytic gradient is the one our backward pass computed. Line them up weight by weight. The analytic row and the numerical row agree, and the worst disagreement across the whole network is about 1 part in 10 million. Pass. No autograd, no mystery. The depth is real and the gradients are honest. One caveat we owe you. The check comes out this clean, because the tan is smooth everywhere. Swap in a rectified linear unit, with its sharp kink at 0, and a finite difference that straddles that kink can spike a single coordinate. Step even slightly off the kink, and it passes again. That is the whole episode. One linear unit cannot bend, a stack of them still cannot, but one nonlinearity in the middle can, and the backward pass you already own carries it. Next time, we hold the body still and change only the head. One body, 5 heads.